have Michael from Northeastern. He's a PhD student, I think a third year, right?
First.
First year. Oh, first year PhD student. Okay. Who's going to be talking about choreographic programming for consensus? Go ahead.
All right, great. Thanks for coming to my talk. And I'm going to be talking about stream choreographies for consensus. This is some in-progress work I've been doing with my advisor, Josh Gancher, at Northeastern. So before I start, I'm going to just quickly talk about consensus. Consensus is kind of a mechanism for getting a cluster of machines to all agree on a linear ordering of events, and all doing that without some kind of single point of failure, like a centralized database. So this is, if you've ever heard like Paxos, Raft, there's also many other variants that do like Byzantine fault tolerance. These are the kinds of algorithms that I'm talking about. And these algorithms are notoriously hard to get correct, which is why there's been a lot of work trying to basically formalize them and reason about their correctness. And so in this work, we're kind of thinking about if there's better kind of programming paradigms to be able to even talk about these in the first place. And choreographic programming is obviously kind of a prime candidate. But as they exist today, there's a lot of challenges for writing consensus algorithms using choreographic programming. So the first is that in many formalizations, choreographies are kind of sequential. So you execute a program, everybody kind of communicates, and then you're done. But servers have to kind of run on forever. So the first thing you might think is, let's just put this into a harness, and then the harness runs a loop. And there's been a lot of work that's already been doing that. The second difficulty is that you need to kind of handle state in concurrent requests. So you can't just run a single loop. The loop has to be able to talk about some kind of persistent state. So if you're thinking about something like a web server, the web server might put the state into a database. And then the database will then kind of furnish your state. But if you're writing the database, as many consensus algorithms are kind of like the core of a distributed database, you don't actually get that luxury. So on top of that, another problem is that a lot of these requests are actually part of sub-protocols. So like in Raft, a node might be simultaneously conducting a leader election, which itself is an entire protocol, while also servicing clients. So you really need kind of a high degree of concurrency. And the final challenge is that there are some patterns in distributed systems that just really hard to express when you have kind of deadlock freedom by construction. So in this work, we're going to explore basically trying to create a new choreographic language, which first of all is able to express a high degree of concurrency. And to follow up on that, we don't want to rely heavily on having a harness that kind of provides the state for us. And so to do this, we're going to use an abstraction called streams. And the next goal is that we want to be able to represent these common distributed systems patterns. So this includes things like quorum and leader election and so on. And for this, we'll use an abstraction called clusters. And finally, we would like to be able to do kind of meta theory with this, like being able to talk about equational reasoning and EPP correctness. So all of this is going to be done kind of using a core calculus. So there's been a lot of kind of prior work on this. If you were here a couple years ago, there's for stream semantics, there's a project called Hydro, which kind of did a lot of this, kind of made a lot of progress in this direction. So we took a little bit of a different approach when it comes to the stream semantics by having a more dynamic communication graph, that's communication topology that's more integrated into the language, so we can kind of talk about the meta theory of the entire language rather than just the communication. And for location polymorphism, there's also been a lot of work in here, but we kind of took a simpler approach, mainly just to make it easier to do meta theory. There's no reason we couldn't extend this our language to incorporate some of these ideas, and we would be really open to doing that in the future. So for the rest of the talk, we're going to kind of go through the main mechanics, and then we'll look at some examples. Right, so first, streams. First of all, there's a lot of different ways streams are kind of formalized, so I'm just going to introduce the way we did it from the start. So I'm going to be using this kind of diagram for our streams. This is kind of like a sender side, and then that side is the receiver. So the receiver essentially gets a source of values, and these values can come from a network, or they could just be kind of produced from like just nothing because you're writing a program. Values can arrive basically any point in time, and they're going left to right. So the 1 is received first in this case, the 2, and then the 3. So this is just kind of the visual language that I'm going to be using for the rest of the talk. And then our streams are also possibly finite. So if you send an end token, then the receiver knows that the stream has ended, and in certain cases, they can kind of go on to the next thing. But it might also not have an end, so it could be possibly infinite for the case of these kind of long-running servers. And of course, we love types, so all of our streams are typed with the values that you send over them. OK, so just to kind of cover our bases, we have a bunch of stream combinators that you can use. A lot of these will be very familiar to you. So when I go over these, I'm going to be showing both kind of like the formal version and also the diagram version. So for empty, we have basically, you can always create an empty stream of any type. And streams are completely local. So we have @L there to kind of show this. We have pure. So pure just kind of returns the exact same element. And it's suggestively named because this is basically the list monad. So we have bind as well. And bind, essentially, you take a stream of values. For every value, you map that to another stream. And then you just take the results and you concatenate them. And this is why end is important, because you need to kind of know when the next stream starts. One important thing here is that bind is lazy. So whenever you receive a value on any of those intermediate streams, that gets immediately kind of pushed out. And so you only react to elements that are received. And this is important because, like, for example, when we go on to write some of our more higher level combinators, like map and filter, for example, will only supply a value to the downstream once you find any element that actually satisfies the predicate, rather than just, like the empty does not produce any value to the downstream. And this is important for our concurrency case, because this means that you can write filters and notify when some kind of event is occurred, but you don't always have to have that. OK. And then the last two I'm going to introduce are also pretty straightforward. So we have scan. This is just list scan. This is important for having state. So in this case, S is a state value that for every single next item is being kind of updated. And in our formalization, we have the stream outputting S as well, just because it makes it easier for for us. And then interleave is going to be this non-deterministic kind of combination of two streams. So you just take whichever value comes first and then combine them into one. So these are our building blocks. These are all pretty much like local operations, as you can see. And with the exception of F, so the Fs in the functions over these are kind of global functions, but we have a type system that restricts. We use the type system to do knowledge of choice kind of restriction, rather than having kind of a runtime thing to kind of propagate it. And this is mostly because a lot of the examples that we're looking at don't actually need to have this kind of branching. We would actually rather make it less kind of expressive here. But we are open to kind of like revisiting this and extending this in the case of like multiply located values. All right, so let's talk about the stream lifecycle. So this is basically we have a receiver side and sorry, this is kind of like the source side, and that's the receiver side. So in this case, we are introducing something called sync. This, if you are familiar with Rust, like async Rust, the name kind of comes from there, but we're doing it a little bit differently. So the sync is kind of where values come in, and then every value that's received on the sync kind of goes to the stream. And the reason why we have these separated is because these can actually occur on different locations. And so when Alice and Bob are communicating, Alice has this sync that she can use to kind of basically plug in values, and then Bob will then receive them. And so whenever you create a sync, you create it with a corresponding stream using a rule that looks like this. And we have this uncoordinated. You're not sending an extra kind of value. You're not sending extra messages to do this. And our type system basically enforces that you can't send things in an unprojectable way. And then the final thing is forward. So forward is kind of the thing that actually sets everything in motion. All of the stream combinators I was talking about, those are actually just building kind of inert values. You're just talking about like building kind of functions, and they're just inert values. And then the forward is the one thing in the entire language that allows you to spawn a subprocess that actually starts listening to it. And so this is, because they start consuming streams, these are actually resources, and we have a substructural type system to enforce that you can't reuse syncs and streams after they're consumed. And so this kind of gives us a way to talk about communication over between different hosts. And the type system kind of is important here, and or the fact that they're just values before they're forwarded is pretty important, because we have a pattern. This enables some kind of pattern called higher order syncs. And so the question is, what happens when you send a sync over a sync, right? So because syncs are just values, you can send them just as you would any other value. So let's run through this scenario here. You have Alice creates a local channel where you have stream and sync pair between herself. You just take that sync and you send it over to Bob over this existing communication channel. And then when Bob receives it, it's just a local sync that he can do with it whatever he wants, as if it was something that he created to begin with. And even though it's on a different location, they are actually still linked. We're going to have, when Bob sends any values, Alice is going to receive it. So Bob can just plug in any stream. It could be a local value. It could be a pure, or he can hook up a stream that's coming from another location. So it could be something that's networked. And so our local semantics basically is designed so that when Bob receives the sync, he's actually doing a little bit of bookkeeping to save where it came from, so that we can figure out how to send it back to Alice. And this gives us kind of a way of gives us a way of talking about composable protocols, because you keep the communication kind of internal. And we're going to see an example of how this works. So here's a part of Paxos that I kind of carved out. You have a proposer sending some things to acceptors, and then the acceptors will, based on like some internal computation, send a result back. Normally, when you do this, the responses are all stateless. So when you get the response, you have to then do a lookup and say, oh, did I send this ballot before? Then I have to add an ID to kind of identify which requests I sent. With our approach, you essentially kind of send the syncs over, and then each of the acceptors are basically doing local kind of forwarding while these are still attached. And the important thing here is that the proposers then are no longer having to wonder where, which request it corresponded with. You already had the stream, and it was like exactly corresponding to the request that they were sending. And so one important consequence is that in one of our distant goals is to use this formalism to do verification and talk about maybe sending proof witnesses over the network that get erased at runtime. This makes it a lot easier rather than having to keep kind of like a global invariance on where these requests came from and then having to match them up. So that's streams. That was kind of the bulk of the language. Then we have clusters. These are mostly here to allow us to talk about communication between a lot of different nodes. And so in our formalization of clusters, we kind of allow, we have every single node is doing the same computation within a cluster. And we basically extend the language in order with these global types in order to do this. So the way these are basically abstractions. You can create abstractions, you can apply them, and these are their formers. the important thing is how they interact with streams. So we'll take a look at this. First of all, if you're in a distributed systems context, you always want to do some kind of fan-out operator. So basically, we have a construct called fan-out, which just takes any stream, local stream, and turns it into one stream for every location in a cluster. And the important thing is that these are all local operations. So you're actually kind of doing this duplication locally, because as you remember, forward is the only thing that can actually initiate communication. And so you would chain this with the forward if you wanted to actually do a send. And so fan in is the exact opposite thing. We have pretty much analogous operation, and it's also local. OK, so I know that was a lot, so let's look at an example of how this works. And so I talked about quorum being kind of a difficult thing to express traditionally. Let's see how it looks in our language. So we're going to have this scenario where you have a list of machines in a cluster, and they're all trying to vote on some outcome. And so in a quorum, you want to take the majority, and then you want to kind of disregard the rest of it. Once you have the majority, you don't care. You can move on. So I'm going to represent this visually and also with our program. You don't have to read the code. It's going to be a little bit dense, but this is just kind of showing how it's built from the primitives that we used. So first of all, we need to get all of these votes into the same machine. So we're going to create these channels to send them all into the same machine so that all of these are located at the same place. So we're going to do the forward on each of those locations. And then we're going to fan them in so that you got one stream with all of the votes. And then from this, from here, you basically have a list of values. So it's just a matter of doing kind of list scan and then doing a filter. And I've left the scan function out, but it's basically if it's true, you add one to the true vote. If it's false, you add one to the false vote. And then the filter only furnishes a value if the quorum is actually achieved. So what that means is that the downstream consumer of this quorum just needs to supply the input cluster and then gets back a stream where once you receive any value on it, that means quorum is kind of satisfied. And so we kind of use this to write our Paxos implementation. This is our DSL and lean so far. There's a lot of code because right now we don't have kind of a rich inference. So the important thing to note here is that we have a type signature for Paxos that is pretty much as concise as you can get it. You have proposers. This is single decree Paxos. And we can kind of chain this and use this externally too. But we have proposers, acceptors. These are two clusters that you pass in. And then for every proposer, you kind of have values that you want to propose. And then the output is also a set of values, but those values have been decided. And so the program that we've written kind of maintains Paxos' safety condition that that only one value is ever decided. And then notably, all of the communication between these clusters are kind of internal to the language. So you don't have to have any kind of external state or harness that manages this. So finally, I want to wrap this up a little bit by talking about the meta theory, what kind of properties that we're going to investigate. First of all, we're going to look at type safety. So type safety, obviously, we have a kind of a type system. It needs to ensure a lot of properties. So we're doing things like progress and preservation. And then also, we want to study EPP correctness. And this essentially requires us to have like a strong local runtime to do all of this. The next thing is we don't actually forbid deadlocks in this code. So what we've kind of noticed is that traditionally deadlock freedom has served multiple purposes. One is that it kind of ensures programs don't get stuck, and then also simultaneously ensures that you don't have deadlocks. And we found that this was a little bit constraining for some of the patterns that we wanted to express. So we wanted to keep the good parts of being able to ensure programs don't get stuck, communication all gets matched up, and there's no sends that don't go to the correct places. But we also want to allow kind of like being able to drop requests that you don't care about anymore, like in the case of quorum. And so because we have a stream semantics that is concurrent, we don't actually suffer from we don't suffer as much when you have things that are just waiting on nothing forever. Okay, so finally, our current progress is we have basically all of these done. For the local language, we're still kind of finalizing the semantics a little bit. And of course, we have our example. And all of this is implemented in Lean as a DSL. So the next steps for us are we're just going to do pretty much the local semantics and the EPP. And I put these in the future work, but really these have kind of been driving the way we've been designing the global language. So it's not like we haven't thought about that at all. And then so as I've kind of hinted at, the distant future for this is we like to use this as a foundation for doing program verification on these distributed systems, because like part of the big problem is that you can't really verify that the Paxos that you've written is correct. So we would like to be able to talk about, in the type system, ways of saying, oh, Paxos does have this guarantee. And that's all I have. Thank you.
Thanks for the talk, Michael. I'm really excited to see more work in this direction. So during the sort of flow era that you mentioned, one of the things we found was most important for us to reason about when talking about correctness was whether or not the order of streams was particularly deterministic, especially when you start combining streams from different sources. Mm-hmm. And I'm not sure what your overall ordering semantics there are.
Yeah, so we have been doing a little bit of thinking. Right now we're, so I think the problematic case for us with regards to that would be like doing a scan over like an interleave. We have kind of considered doing something similar to what Hydro did, where we have like some kind of unordered stream versus ordered stream, but so far direction we haven't really kind of made decisions there yet.
Well, I'm happy to talk about it anytime.
Hi, thanks for the talk. May kind of stole my first question, but I'll ask my second one instead. Okay. Oh shoot, what was my second question? It might come to me in a moment.
Sure. I just had a clarifying question around the terminology of sync. When I think of signal flow analysis, I'm thinking sinks and sources and sinks. Yeah. And it looks like you have a sink that is like sending messages. So I find that kind of confusing or problematic. And it seems that your use of the word sync looks like a named first class channel that you can pass the channel in a process calculus kind of way. And I don't know if clarifying is all.
Yeah, the name really comes from, like, initially when I was thinking about this, I was thinking in terms of kind of Rust's async. I'm not married to the name, so we could, if you have a better name suggestion, we could kind of
channel.
Kind of.
Anyways.
Yeah, we can talk about it.
I love naming things.
So So one of the nice things about choreographies is you know exactly how many messages each party is going to receive along a particular protocol, at least within a particular branch of computation, right? Mm-hmm. So, and when you have this abstraction of streams, you kind of lose that, right? Because you might have somebody who, it sounds like you can send like a sync over, and you can just send some arbitrary number of messages. Yeah. The question is, do you have any way to, for example, say I have a stream, this will receive exactly one event, or at most one event? And if not, do you have any thoughts on how you might support that in the future?
Yeah, that's also a direction we've been thinking about. We haven't needed it for our current example, so we've been not really kind of added that to the type system yet. But I can imagine we would have like 0, 1, or infinite kind of type system, but like stream length kind of thing, and then all the operators would have some kind of interaction with that, but that's all still kind of under investigation. Our primary kind of goal is to be able to just see if we need any of these conditions for our EPP, and if we do, we might expose them into our surface type system.
Okay, maybe last question. So I love this work. I think it's so important to be able to express consensus in choreographic programming. But the one thing that I had to do to get published in the first place was say, like, well, we give you deadlock freedom by design. We give you that. And you've lost that. So what are we going to do to convince people that this work is useful if we don't have that, thing to advertise?
Yeah, I think deadlock freedom is kind of an important thing that we can consider, but the way we would like to kind of consider that in relation to this work is to be able to have kind of like a separate analysis for that instead of making that part of the language, because that then reduces expressivity about what you can write.
I have an answer for that one, which is something that was inspired by something Andrew said, which is we want a better definition of deadlock freedom that lets us still write the programs we want to write. Better meaning weaker, but we can use it better instead.
Sounds like
Yes.
sounds like a great conversation to. Oh,
Yes.
yeah.
That's the word.
We can take this conversation into lunch. Let's thank the speaker one more time.
Thank you.